This is the counterfactual fairness replication. My name is Oliver Penglaze.
My name is Gautam Kotluri.
My name is Mingfei.
My name is Kai.
There are many machine learning algorithms that can do automated decisions for complex issues such as receiving a loan, insurance pricing, predictive policing, prison sentences, etc. The paper we used for this project, the writers seeks to develop a way to address whether a prediction is fair using tools from causal inference. Through causal modeling, we can see how and where this unfairness is happening because algorithms use observed data to make predictions, data that may contain historical biases, and as it can often result in unfair policy decisions. Next slide, please. To understand how we evaluate fairness, we must define what it means. Below are definitions presented by the authors. Fairness through unawareness. An algorithm does not use any protected attributes. If we have observations of a person's race or sex, we just ignore that information. And individual fairness. An algorithm gives similar predictions to similar individuals. And a demographic party. An algorithm gives the same prediction no matter what the value of given predictor is. And equality of opportunity, algorithms give the same prediction given the outcome regardless of the protected attributes. And the last one is counterfactual fairness. Had any individual been of a different race, sex, etc., the predictions would not change. The authors believe that the counterfactual fairness is the correct definition to use because we can make comparisons on an individual level. We are asking what would have happened if this same person was of a different race or sex. Next slide, please. Below is a simple example from the paper to show how counterfactual awareness works. We are looking to predict the accident rate of an individual given we have observations on some protected attributes and the color of their car. And we have a simple DAG right here, and we have 4 attributes. The first one is a protected attribute. So it means any attributes that should not be discriminated. And X is the observed attribute, which is the red car. And Y is the outcome of interest. It is the accident rate. And the U is the latent variable, which means aggressive driving. In this example, some group A is more likely than other groups to drive a red car, but are not more likely to get into an accident. However, people who are more likely to be aggressive drivers like to drive red cars as well. We are modeling a discriminatory effect as a causal effect. If we were able to predict who would have a high accident rate Y by using just X, we would have a counterfactual unfair prediction because we know that individuals of the protected attributes like to drive red cars more than other groups, even though they don't get into more accidents. One of the main implications of counterfactual fairness is that a prediction will be counterfactually fair if it is a function of the non-descendants of A. In the example above, we could not use the observed attribute red car to make a counterfactually fair prediction, as any changes in A would cause a change in the observed variable red car. Instead, we would want to try to infer the latent variable U. This is not an if and only if statement. However, it is possible for a prediction to be counterfactually fair if it is a function of descendant of the protected attributes A. However, this is only true if the dependence of the prediction on the protected attributes disappear in a function. Then we have a fair learning algorithm. Essentially, what the algorithm is saying is, given the observed values of A and X, extract the values of the latent variable U and then use those variables in the predicted model. And we have 3 different levels of assumptions that make counterfactual fairness possible. The higher level requires strong assumptions. Here is our level 1, level 2, and level 3. The author recommended always modeling the causal structure to reach the goal of counterfactual fairness. They state we are essentially learning a projection of T into space of fair decisions, removing historical biases as a product. Modeling in this way does not always give the most accurate predictions. However, this is not the goal of the procedure. The goal is to accurately model the real world, including social biases that may arise, and to use causal modeling tools to address algorithm unfairness. The following is another example of this in practice.
Thank you, Mingfai. We have considered the example of law school success to implement the algorithms discussed in the paper. In this example, the law school wants candidates with good knowledge to succeed in the law program. However, knowledge is an unobservable variable. The challenge was to make sure the admissions process was fair to underprivileged groups. The college admissions panel doesn't use candidates' racial or gender identity in determining whether to admit them into the program or not. They would only consider the undergraduate GPA and LSAT score to keep the progress fair. However, the admissions panel's decision might get indirectly influenced by protected attributes like race and sex. Students from less privileged background may lack the economic opportunity to enroll in LSAT preparation courses. The classroom performance may not depend on knowledge alone, but also be unduly affected by sensitive attributes that we do not want to use as a bias for admissions. In this project, we implemented concepts like fairness through unawareness and counterfactual fairness as discussed in the paper. We leveraged these concepts to identify historical biases while estimating knowledge. We built a structural causal model using the tag shown to generate samples. These samples are used in the aware and the full model. We have constructed the structural causal model in Pyro using the tag discussed in the previous slide. The probability assignments for the simulation are made up as there was no simulation-specific information given in the paper. Race, sex, and knowledge are considered as exogenous variables. A probability of 0.7 and 0.35 are assigned for race and sex respectively. The knowledge is drawn from a standard normal distribution. On the right, we can see the equations that we have used to generate the synthetic data. We have considered the race and sex as binary variables. Knowledge is a normally distributed variable indicating an applicant's unobserved knowledge or ability. LSAT is a normally distributed variable, function of race, sex, and knowledge. GPA is a normally distributed variable, function of race, sex, and knowledge. So GPA basically means prior to the law school GPA. FIA is a normally distributed variable, function of race, sex, and knowledge.
For the full model, we use all available observed variables in the model. This includes race R, sex S, LSAT L, and GPA G. We can later use this model to more accurately reconstruct first-year average F, as it uses race and sex. The paper notes that because it uses all the observed variables, this model achieves the highest accuracy. However, it is clearly biased since it uses protected attributes, race and sex directly in its decision-making. The other model we use is the unaware model. If an algorithm is fair so long as any protected attributes in our example, race and sex, are not explicitly used in the decision-making process, unlike the full model. However, it has a clear shortcoming as elements of X can contain discriminatory information analogous to the protected attributes that may not be obvious at first. To replicate this model, we have considered only the attributes GPA and LSAT. This is the same model used initially by the law school, assuming a fair admission policy. The first-year average is predicted using the GPA-G and LSAT-L from the DAG. We can understand that it is indirectly biased because of the race and sex are also affecting the first-year average. The resulting density plots look similar to the full model as the unaware model is still making biased decisions, but less openly in its training. Next slide, please. Here are the density plots. We have created the linear regression model and selected the MSE as the loss function. Here is the resulting density plots from the trained samples separated out by the predicted attributes. This plot is the density plot for the full model. And next slide, please. And this is the resulting density plot from the unaware model. As we can see, both of these models are not counterfactually fair, as we'd expect the blue and orange plots to overlap if they were.
To counteract the biases, instead of using the biased attributes GPA-G or LSAT-L directly, we use these to infer K, which is their parent, the unobserved latent variable representing law knowledge. However, as a parent of G and L, it is unaffected by the protected attributes race and sex. Since it's also unobserved, we must infer k and use its posterior distribution. When we compared our posterior k values to our simulated data, or the ground truth of k values, they came very close, and you can see these distributions on the right. So using this posterior distribution of k, we can now predict the first year average. This model is the level 2 model described in the paper. So here are the density plots for the first year average for our FAIR model. As you can see, the first year average is the same for race equals 1 versus race equals 0, and when sex equals 1 or sex equals 0. However, the paper does note the FAIR model's accuracy is worse than the full models, for instance. However, because these distributions are now similar between race equals 1, race equals 0, or sex equals 1, sex equals 0, there's no more of that indirect or direct bias that was in the unaware or the full model.
After the previous implementation of the counterfactual fairness, we take the protected attributes into consideration, so we are able to take into account the different social biases that may arise towards individual based on sensitive attributes and compensate for these biases effectively. In our implementation, we are able to capture these social biases and make clear the implicit trade-off between prediction accuracy and the fairness in real-life situations. We believe that the fairness should be regulated by modeling the causal structure of the world. Simply relying on probability independence cannot meet the fair standard. It also cannot point out why and how unfairness is occurring. By using the models we have, we are able to provide practical solutions for solving a wide array of fairness modeling problems.